Swayam Prabha. Digital India. Educated India.
Hello everyone, let's get started. So in the last lecture we were talking about plasmonic metasurfaces, and I told you that we understand plasmonic resonances and they enable extremely high confinement of electromagnetic energy. We can confine light down to few tens of nanometer scale. And I said that okay, this sort of confinement is useful for propagating energy on a chip. And it's also useful for various other applications like, let's say beam bending or sun sensing and so on. Okay. But plasmonic metasurfaces also suffer from one drawback. That is the inherent loss in the metal. We have seen that we choose either silver or gold because they exhibit extremely low loss. But even then, that can be significant in some applications. Okay, in that kind of a scenario, it turns out that dielectric nanoparticles or dielectric nanostructures are useful. The reason is we can try to engineer the response in such a way that the dielectric structures have extremely low loss, and they can be useful. All right. So I have shown this slide in the past. We have considered what happens when you have electromagnetic wave incident on a sphere, let's say. So I talked about the Me theory, I think in the week 4, where we discussed plasmonics. And towards the end, I also just briefly flashed this slide wherein, we can calculate the scattering cross sections. So for example, if you have a electromagnetic wave incident on the sphere, it scatters. But how efficiently it scatters is essentially captured by scattering efficiency, and that is what is shown here. And so you have various peaks, and I briefly talked about, the modes that are there. You can have electric and magnetic resonances that are there. Electric is a typical, dipole and the quadrupole. But in addition, you can also have circulating currents, displacement currents inside the nanoparticle that can give you magnetic dipole, magnetic quadrupole, and so on. And those are the peaks that we have identified here. Right? So we talked about this, and this is exactly the same Me theory that we've used. We just replaced the dielectric constant of a metal with a semiconductor or semiconductor, high index semiconductor, for example silicon or gallium arsenide. You get these curves. Okay, the only issue is the size of the nanoparticle is quite large. For example, here the silicon sphere diameter is about 200 nanometers, and we have already seen that for plasmonic structures, plasmonic resonances, the sphere diameter would be something like 50 to 100 and so on. If you go to larger diameters, there's a redshift of the resonance. Okay. So this is essential. This Me resonances in dielectric nanoparticles are very critical to dielectric nanophotonics. So I just wanted to review this. Okay, but how does the dielectric material help? Okay, when I say dielectric, I use it in a very loose sense. For example, if you are very precise, then you will say glass is a dielectric, but silicon is a semiconductor. But for me, I'm referring to both glass and let's say silicon also as a dielectric, because the band gap is large. They don't have any intrinsic, there's no conductivity, and even if there is some carrier density in the semiconductor, it's a doped semiconductor, and then the free carrier density will give rise to true response, and the other part of it is a dielectric response, which is coming from, let's say, intrinsic semiconductor. So I use this term when I say dielectric, I mean both doped semiconductors and also insulators. All right. So I already mentioned loss. Okay. So we have this traditional plasmonic resonances. So you excite the plasmonic resonance, and you can also have the split ring kind of structures wherein there's a circulating electric field, and that causes a magnetic field. And I mentioned that these structures suffer from loss. So this is an example here. So basically, this is the loss for gold and silver plotted with respect to wavelength. And you see that a silicon loss is quite low. You might say, oh, silicon should actually have loss up to 1100 nanometers. Why is the loss low? Well, it turns out that silicon, you can also make amorphous silicon. If you have amorphous silicon, it has a band gap of about, optical band gap of about 700 nanometers. Anything above that, it's lossless. All right. So yeah, then there are other materials which can have low loss. So That's why, one of the reasons, people have moved towards dielectric nanophotonics in the last 6-7 years. So starting roughly about 2015 or so, this trend started. Another advantage of dielectric materials when compared to metals is that they are CMOS compatible. So what I mean by that is you can use the traditional, foundries, the standard equipment that we have in the clean rooms and all that, we can use it to fabricate the structures. So the patterning quality can be much better. If you want to pattern metal structures, you'll have to do a process either called as a lift off or, focus and beam milling and so on, which can be a little bit tricky and it not scalable. But for dielectric structures, I think we can use the standard CMOS techniques very easily. And the CMOS compatibility is also referred to as, sometimes people talk of it as, you can fabricate these structures in the standard fabs. Well, yeah, that is possible. There are some caveats anyway there. All right. So that is the second advantage of dielectric structures. The third advantage is the presence of these unique modes. When we talked about the metal nanostructures, we only mentioned the plasmonic dipole essentially. Okay. And if you have a large structure, then higher order modes come into picture. But there are no magnetic response. There's no magnetic response in metal. Okay. Unless you actually create something like a split ring. Okay. But if you look at dielectric structures, as for example, a silicon sphere, it has an intrinsic magnetic dipole, and that can give you a very nice design space for you to engineer the response. Okay, the presence of this electric and magnetic dipoles together can be useful. Why is it useful? Well, one of the applications could be to engineer directionality. When we studied the dipole, we understood that whenever there's along the axis of dipole, there's no radiation, and the radiation only occurs perpendicular to it, like a donut shape, right? That is with a single dipole. Suppose if I'm looking at it in this direction, there's forward and backward radiation, which I don't like sometimes. I want only unidirectional propagation so that I can efficiently transfer my energy in one direction, right? So such a thing is not possible with a pure electric dipole. You also need a magnetic response. Either you engineer it with, things like split rings, but then how do you make both of them overlap and all becomes an issue, or you have to have multi-layer structures to engineer the magnetic response. In any case, if you have both electric and magnetic dipoles, I can orient them perpendicular to each other, and I'll see that the emission the scattering becomes predominantly in one direction. For example, here we are, let's say, having such a scenario where you have combination of electric and magnetic dipoles. There's an incident radiation, and it is getting scattered only in the forward direction. So this is one application. I can think of geometries where you have contributions, differing contributions from these electric and magnetic dipoles, and that can even cause backscattering to happen. All right. So these are the various advantages of having dielectric nanophotonics. If you're interested, you can actually look at the review published by Arsenic and others. All right. So, and with these structures, people have realized, starting roughly about 2015, that a lot of applications are possible, and some of them are just briefly mentioned here. So one application could be beam bending. We talked about the beam bending in metal nanostructures. There the problem again is efficiency. How much are you able to actually get into a cross-polarized light? Cross-polarized beam and so on, and the losses of metal also play a role, so you cannot get very high efficiencies. But with dielectric structures, researchers have shown that you can in principle have bending in whichever diffraction mode you want, and then that beam bending has been demonstrated. You can also use it for focusing light. Now, for example, like a lens, I'll talk about this in a little bit detail in the next slide. And then you can also generate these vortex beams. We saw the donut shape profile that we created with a plasmonic metasurface. A similar thing can be done with dielectric surfaces, and even more richer variety of structures can be generated, or structured light can be generated. You can create holograms and light, structural color. So you just, this looks like almost like a real color, but then this is actually, if you zoom into it, it's all structural color with various antennas which are arranged in a particular shape. And there's also things like fluorescence enhancement that we can create, because a semiconductor can actually give you fluorescence. And if you engineer the nanostructure, you can actually create much more efficient fluorescence. So some of these applications people have looked at. So I would not be able to go into details of many of these things. So what I'll do is I'll pick 3 different applications, okay, to try to give you a flavor of what is the research about. The first one is what is known as meta-lenses. Okay, so if you look at any traditional microscope, the standard microscope that is used in the biomedical community or even in physical sciences, they have an objective. Now this is an objective that I picked up from the internet somewhere, the Edmund optics objective, and those are very highly engineered pieces of equipment. The objective itself can be quite expensive depending on what sort of features it has, and the reason is it has a lot of parameters that are important. The working distance, the magnification, and so on. Whether it's immersion or normal air, and lot of things. The numerical aperture, how much of light is it able to capture, and so on. So to create these objectives, people actually use multiple lenses. So if you look at a cross section of this objective, there will be many lenses which are precisely aligned to get maximum performance. But then it turns out to be quite big. For example, it would be of the size of 2 or 3 inches, maybe 4 inches. 2 to 3 inches is what I would say it would be. Okay, so can we make it smaller? That's been one of the limiting factors for all the imaging equipment. If I want to, let's say have a compact imaging system, then yeah, I would like my objective to be smaller. Similarly, in the cell phone, I have these lenses which are focusing light from outside onto the CCD camera and CCD inside. So can the lenses on the phone be smaller? So there are a lot of applications where you don't want thinner and more efficient lenses. So one of the ways to create that is by using the ideas of metasurfaces. So here is a picture of basically a circular arrangement of nanostructures. If you zoom into some small section on the edges, you will see something like this. So these are essentially titanium dioxide nanopillars which are arranged in some fashion. The angle of rotation of the nanostructure here gives a different phase, and that's called as a geometric phase in the literature. So essentially what you can do is we are mimicking the typical lens. For example, if you have a standard lens, you have a convex lens like this. So in the center, you have a large phase shift that is the beam slows down by a significant amount because there's a thick glass. On the edges, you have a thin glass, so the phase advances, and then overall the phase envelope actually becomes curved, and it starts to go and focus on a particular point. So similarly, if you engineer phases in this, this was originally done in the context of optics, in what they call as Fresnel zone plates. So essentially, you have plates which are having different phases along the circumference, and then you can actually focus light and things like that. So people have tried this, and this is work from Professor Capasso's group, again from Harvard. So they showed that with these dielectric structures, you can actually create a focused light, and they're comparable to the standard objectives. Of course, there are some limitations of these lenses, but still, considering the size, this is, I said, 2 inches. This will be about, I think, roughly lambda by 2 or so wavelength. I mean, roughly in that on the order of wavelength height. Okay, so you're able to get focusing. So you're able to. So they have demonstrated that these lenses are possible all over the visible wavelengths, and this is basically an image of a standard reference. That if you image and you show that it's clearly imaged, that means you're able to resolve features very well. So they showed that you can actually fabricate these lenses for blue, green, and red, and so on. So over the visible wavelengths, you can fabricate these structures. So, and I think there's a lot of interest in trying to do this because this can be useful for a lot of AR and virtual reality applications. I would like to have a lens which will only focus on my eye, but others cannot see. I mean, a lot of things can be talked about in this context. Okay, so there is a lot of interest in this. So this is one application I wanted to talk about. Another application I want to mention is much more fundamental, I would say. So all of us have heard about Brewster angle. If I ask you what Brewster angle is, from let's say, you'll say that, when light is incident on a material like glass, the reflected ray is polarized, and essentially at that Brewster angle, there won't be any p-polarized light. The p-polarized reflection becomes 0. So for example, I have a particular angle of incidence, and then this exiting beam, if I have reflection beam, this will be S polarized. Okay, the transmitting beam will have both S and P polarization. The reason this happens is, if you go back into the basics, the incident electric field will actually excite dipoles. And when this reflected ray forms an angle of 90 degrees with the refracted ray, what happens is the dipoles are oriented in this direction, and then there is no emission in that direction for the p polarized light. So only S polarization remains. So no emission from p polarized dipoles. Okay, if you looked at it just even maybe 10 years back, people would have said, most of the people would have said, oh, Bristol angle is something fixed. You just take the tan inverse of the refractive index and you get that, and that's what it is. So in the top, these two figures are both for optically for just epsilon not equal to 1, mu equal to 1. So basically they are not magnetically active. All right, but then with the idea of these metasurfaces, it turns out that Brewster angle is no longer a material property, fixed material property. You can actually engineer. The way we can engineer is, I'll excite, let's say, instead of just this pure electric dipoles, now I have, let's say, in a dielectric structure, I can excite both electric and magnetic dipoles, and I can look at the conditions. I can carefully design the resonances and the geometry. I can take these resonances and arrange them in a lattice, and I can carefully engineer the sizes and the periodicities and so on, such that I can have zero reflection in both S and P polarized light. Okay, so this was a nice experiment that was very nicely explained by Ramon Paniagua Dominguez. He's at A-Star, and then the A-Star team had done the measurements, and then later he explained this very well. So you can look at this paper for the details. So just to tell you what it is, I'm just showing you the simulation results for a couple of for different scenarios. So you see here, this is a reflection for P polarized light, and this is the P polarized light, which is going to 0. The reflection is going to 0 at a particular angle, and you would call that as a Brewster angle. Now you see that for various wavelengths, that angle at which reflection goes to 0 can change. In principle, you can even go below 45 degrees. If you take simply a glass, you would say that the Brewster angle is what, 57 degrees? No, sorry, tan inverse of 1.5 is how much? Arc tan. Anyway, so you'll see that it's 56 degrees for 1.5 index. But then even if you can even go much below that, and this you can do for P polarization, and this is for S polarization. S polarization also, you can have a Brewster angle, means at which the reflection goes to 0. So that can occur at different wavelengths, and this can be done with arrays of dielectric spheres. For example, silicon spheres, or you can even just make discs out of it. In this paper, they have experimentally considered discs. What happens when you arrange a series of discs? They've shown that you can have this Brewster effect, and they called it generalized Brewster effect. So you see, whatever was taken as a kind of a law not very long ago is now just one special case, when basically you have this magnetic response as well. So in these two cases, you have both electric and magnetic responses. So combination of these two things can actually give you newer functionality. So this is the second example I wanted to show you. And the third example is, again, the beam bending that we talked about in the context of plasmonic metasurfaces. So in this case, we can also have dielectric structures. So in the plasmonic resonances or plasmonic metasurfaces, we are exploiting the idea of resonance. That is just one way of introducing the phase. You can also introduce a phase gradient by just letting it propagate along a nanowire. For example, if I just take this sort of a structure wherein I have a high index material, which is one pillar sitting on top of a surface, the extent, the diameter of I can change the diameter of my pillar, and then that will introduce various different amounts of phases. So this is one calculation done for diameter of a cylinder on the x-axis and the relative phase that is introduced along as light propagates along the cylinder. So this is, I think, for a fixed height of 460 nanometer height. So you see that as the diameter increases, the phase is changing, and that's going from, we can, depending on the length, you can go from 0 to 2 pi. Okay, we can choose different structures. So what we have done was, we picked up 4 different points on this, 4 different diameters, and then arrange them in this fashion that, along the, let's say if I call this as the x direction, you have a phase gradient along the x direction. In the y direction, there's no change. When I have phase gradient, we already saw that the light bends. Okay. So now the interesting part is, by this structure, we were able to show that you can have bending at a particular, in a particular diffraction order, and only in that direction. If you want to, we saw that if you have a typical grating, you will have incidence like this, and there will be 0th order, there will be first 0, +1, -1, and so on. But because we have introduced a phase gradient, the light tends to go in a particular direction, and that is what is shown here. And it also turns out that this can be shown both for S and P polarizations. The measurement data is shown. And if you look at the relative efficiencies, the amount of light going into a particular diffraction order compared to the overall transmitted light, it can even reach up to 70 to 80%. So that's very high efficiency of beam bending that can be shown with dielectric metasurfaces. So these are three different examples that I wanted to take to convince you that dielectric metasurfaces are something that is exciting and people are looking at. Maybe, who knows, we can pick up some of these ideas and apply to something else. So the whole idea of metamaterials has opened up a lot of interesting prospects, wherein we go and relook at some fundamental ideas and we try to analyze and see what happens. So with that, I would like to close the discussion for today, or this week. So in the next week, I would like to talk about tunable and active metamaterials or metasurfaces. All right. So I'll see you next week. I hope you're enjoying the course, and if you have any questions, I'll welcome. Please post it on the discussion forums. We'll be happy to answer. If you need some help, we'll have one-to-one interactions. I can't emphasize this enough. All right. So, all right. We'll see you. Thank you so much. Bye.